So let's begin Chapter 3. Chapter 3 contains two basic ideas, exponential and logarithmic functions. There's some subgroups on this, but here's the big break that we've got. Up until now, we've been studying algebraic functions, which are just add, subtract, multiply, divide, and some of their related things. Multiplication is related to raising to powers, or exponents. Divide is also related to taking roots, so square root, cube root. So that was everything that is algebraic functions. We have variables, we have constants, and one of these, a variable or a constant, is always the base. So the new thing that we're getting into in Chapter 3 is the idea of transcendental functions, which sounds very important, but we're just using the word transcendental to say it is beyond all the algebraic stuff. And the beyond is a very simple thing, and it is that we've got the variables, the x's, as the exponents now. So what does that look like? Here are the two things. Exponential functions, here's my exponent, and that is the variable. A and B are both constants, meaning those are actual numbers, and we'll be able to solve for A and B and leave the y and the x where they are. Logarithmic is really just looking at an exponential function from the other end. Logarithmic functions answer the question, what was the exponent? So you can see that we've got the x again, but it's not raised to a power. It's not a superscript. It's on the same line as this word log, which stands for logarithmic. And you also have the little b here is the same b that we're talking about over here. And b, coincidentally enough, stands for base. So sometimes you have to tell somebody what base you're using when you're evaluating a log. So let's get into this a little bit. The logarithmic functions start in section 3.3. Today we're just going to talk about exponential functions for 3.1 and 3.2. So here are some of the versions of exponential functions. You have, as we said, the general form is y equals a times b to the x. So one of the things that we use exponential functions for is modeling growth and decay, like radioactive decay or maybe population growth, especially unrestricted population growth. So this is the exponential function general form, and if you want to skip over to page 252, that's where I am. A couple of things we need to note here. A can't be 0. Why? Because then the whole thing would be 0, and then you have no function at all. That would just be a constant function of y equals 0. B has to be positive. And as you go through a table of values here, you might start off with y equals a times b to the x, and you'd say x can equal 0. Well, hey, wait a minute. Anything to the 0 power is just 1. So for this moment in time, when you choose x to be 0, then you get y equals just a times 1. And this is a special situation, and we say that a is the initial value. So before any growth, before any decay happens, that's a result of this exponent being something besides 0, we get a as the starting value. So you'll hear problems like, we've got a population of 800,000 people, and after 3 years, what is the population going to be if it grows at a certain rate? And so a, we know, would be that 800,000, and our rate is going to be the b, and we keep the x where it is. So this would be 1 year, or 2 years, or 3 years, but when it's 0 years, this term cancels out, and this is our initial value. So now let's try to identify some of the exponential functions. Is a an exponential function? Yes. By the way, what is the initial value? Well, we have to have a times b to the x, so there's actually an invisible 1 here, and so we got initial value is 1, and the base, of course, would then be 3. Part B, f of x, it should have been g of x. G of x is 6x to the negative 4. Not a exponential function, because we needed the x to be the exponent, and that's how we get exponential functions. What is this? This is just a power function because there are no other terms here. So the most basic form of a polynomial function. Letter C, h of x is negative 2 times 1.5 to the x. Yes, that is an exponential function. What is the initial value? Negative 2, and the base is 1.5. Letter D, k of x equals 7 times 2 to the negative x. That is an exponential function. Initial value is 7, and the base, this is a little tricky on the base. We have to rewrite this so that we get sort of a positive exponent. Now, watch this. This is a little magic. 2 to the negative x can be rewritten. And if I have 2 and then my exponent is negative 1 times x, well, I can write that out. Negative 1 times x. There's my exponent. I just expanded it a little bit. That actually means that I've got one base with 2 powers, and I can write that as 2 to the negative 1 to the x. Because powers of powers, I multiply them and write the base just once. So now, what is 2 to the negative 1? Well, that would be 1 over 2 to the positive 1, and all of that to the x. So this is actually 1/2 to the positive x, and so my base, tricky, is 1/2. So beware of negative exponents. You're probably going to have to rewrite them to have to get that negative to apply to the base instead of to that variable. And then letter E, q of x equals 5 times 6 to the pi. No. There's not even a variable in there. So it's actually just a constant function because pi is a number, 6 is a number, 5 is a number, no variables. Now you can try evaluating some exponential functions. Here's our original function, f of x equals 2 to the x. So if I ask you for f of 4, that means you're going to write 2 to the 4th power, which is 2 times 2 times 2 times 2, which is 16. F of 0 would be 2 to the 0 power. Anything to the 0 power is 1. F of negative 3, keep the base. Exponent is now negative 3. And there are 2 ways that you can think about this. Anytime you have a negative exponent, you can rewrite it as 1 over that thing with a positive exponent. So now I've got positive 3. Sorry, that's not very clear. 2 to the positive 3. So this is one way you can handle that. Or in the previous example where I said it's like having 2 to the negative 1 times positive 3, then you can rewrite this 2 to the negative 1 to the positive 3 power, which would be 1/2 to the 3rd. Either way, you will arrive at the same answer. So let's do this. I'm going to use this way. 2 cubed is 2 times 2 times 2. So that would be 2 times 2 is 4, times 2 is 8. And 1/2 to the 3rd power would be 1/2 times 1/2 times 1/2. And that, of course, is 1/8. So now, how about this one? F of 1/2 would be 2 is my base, and then my exponent is 1/2. Do you remember that fractional exponents are actually roots? 2 to the 1/2 can be written this way. 2 to the numerator becomes your exponent on that base, and the denominator is your root number. So 2 to the 1st, there's the numerator on the 1/2, and the 2 would be the root number. So the square root of 2 is just the square root of 2, which is about 1.414. This is the most precise answer, and so we'll stick with that. Then how about f of negative 3 over 2? So that's 2 as the base, and now I've got this negative up here. So I can rewrite this as 1 over 2 to the positive 3/2. Now, what does that mean? Hey, it's a fractional exponent, so the denominator is my root number, and the numerator is my exponent underneath that root symbol. So I'm going to write 2 to the 3rd, and then it's the square root of that. So simplifying that, 2 times 2 times 2, that's 8. And I'm still taking the square root, so the square root of 8, and this is still, sorry, part of a fraction, 1 over the square root of 8. Turns out it's about 0.35, but this is the most precise answer. We'll talk about getting square root signs out of denominators. That's called rationalize your denominator, but I will continue with the main exercise right now. Now, of course, you're going to have to solve for some of these things and come up with the actual equations for these formulas. So here are the, here's one way to start. Say we have a table of values. Here are my x values. Here are my y values. So for one function, I've got these y values. For another function, I've got these. So we're going to analyze these one at a time. G and h are really unrelated. We just didn't want to write out 2 separate tables. So I know that these are exponential functions, and so for g of x, I'm looking for things to fill in here. How do I find the a? How do I find the b? Start with the a. A happens when x is 0. So over here, here's my table of x values. Here's my line for x equal to 0. And my answer for g of x is 4. So when x was 0, that's b to the 0 power, so all of this turned into just the number 1. And that leaves me with 4 as my answer for g of x. So a is 4. Then, how about the b? Well, if we know this much, g of x equals 4 times b to the x. How about if we choose x equal to 1 and check the table? So now I'm going to write this. G of 1 would be 4 times b to the first power, and I know that answer. When x is 1, g is 12. So 4 times some base to the first power, which is just the base. So 4 times b is 12. That's my answer for g of 1. So divide both sides by 4, and I get a base of 3. So for g of x, now my answer was 4 times 3 to the x. Is anybody waiting for me to simplify that and say it's 12 to the x? Right, you're not going to have that happen because order of operations. 3 to the x, that's an exponent, and that has to be resolved before the multiplication of 4 times 3. So this is as simplified as you can get it. Now, how about h of x? Well, we're going to start in the same place. For h of x, I've got the same basic formula for exponential functions, and I'm going to start with the a. A happens when x is 0. So where is that? Here's my line for the zeros, and h of x is 8 when x is 0. So that means b to the 0 is 1, and the rest of the answer comes out to be 8. So a has to be 8. That's called the initial value. Then how do I find the b? Well, I can set up the b question with choosing x equal to 1. So I get b to the first power, which is just plain b. So let me write that. h of 1 would be a, which I already figured out. My initial value is 8 times b, which I don't know, and the exponent on this case, in this case, is 1. Now I have that answer right here. When x is 1, h of x is 2. Okay, so h of x would be 2 when x is 1. So b to the first power, that's just b. And so I've got 8b equals 2. Divide both sides by 8. b is 1/4. Huh, interesting. So I can now write this equation for h of x as 8 times 1/4 to the x power. Now, it's time to make a connection here. When we had g of x, the base was 3. And look at this. Our numbers, as our x's got more positive or bigger, so did the y values when the base was 3. Okay. Contrast that with h of x. When x's increased, my y values decreased. And the base was what? Oh yeah, 1/4. So now we get to make some observations here about what is happening with the base and what we can decide should be happening with the y values. Now we're ready to talk about the idea of exponential growth and decay. From that table, you saw that as the base was, I don't know, you'd call it a whole number or something big, then you get growth. And when it's a fraction, you get decay. So let's write this out as a little bit more of a scientific mathematical expression. And this is what we get. When you have an exponential function, here's one other way that you can write this. F of x plus 1, when our original f of x was just a times b to the x, this result of adding one more to that exponent is the same thing as taking the base and multiplying it by the last y value that you had. So think about that. If I'm talking about a very, very simple function here, so let's say f of x was just 1 times 2 to the x, so I can write that as 2 to the x. And now I'm going to say x should be 3. So I'm going to write f of 3. Well, that would be the same as 2 to the third, which is 2 times 2 times 2, so that's 8. Now, here's the cool thing. One other way that you can define exponential growth and decay functions is by saying, if I add 1 to that, so now I'm talking about f of 4, it should be the same thing as taking my base, so that's 2, and multiplying it by the last answer that I got. So what's 2 times 8? Yeah, 16. Isn't that the same as 2 times 2 times 2 times 2? Oh, yes. So this is one other way that you can set these things up. Now, here's the big deal. Right here is the real key to understanding exponential growth and decay and how to tell the difference. So this looks like a lot of math. Let's unravel this. A greater than 0. A greater than 0. Oh, so they're both A greater than 0. What does that really mean? It means that A is positive. Now, because this is exponential growth and decay, I want you to jump up and down and show me the first time somebody hands you a problem and A is negative. I just don't think it's going to happen because we're talking about the initial value. This is a population. This is how much radioactive plutonium you've got. This is how many bacteria are in a population. And we just don't start counting things as negative numbers. So A is going to be positive. So the difference comes with our base. When the base is greater than 1, so 2, 3, 4, whatever you've got, when the base is greater than 1, we say that the function is increasing. And we get something called exponential growth. A quick version of that graph will look like this. And over here, we've got the other case. B is less than 1. So this would be all of the fractional things, like B is 1/2 or B is 1/4. And this also includes when you have those negative exponents, because that negative exponent makes your base a fraction. You've seen me do that twice. So this is called a decreasing function when we have a base that is less than 1, and we call that exponential decay. And the b, this base, can actually be thought of as the decay factor. And over here, I think I skipped this part. We said the function is increasing when b is greater than 1, so we call that exponential growth, and b, the base, is called the growth factor. So let me just finish up here. We've got a graph, very basic graph, and look at that. We sort of reflect it over this y-axis when we change where the base, how big the base is, or when it's a fraction versus something greater than 1. Now, how about transforming these exponential functions? Well, the graphs are going to behave like all the polynomials that we did with the vertical translation, moving it up and down, and the horizontal translation. Now, the trick that we are using here, or the decision-making paradigm, is that when you do something to the x before continuing with the rest of the equation, that will be a horizontal shift, right and left. And the shift goes in the opposite direction of the sign that you're seeing here. So 2 to the x minus 1 power would actually be a shift to the right, or the positive, by 1 unit. So if you have the original moving like this, now we pick up that whole thing and slide it over. Doesn't look like I slid it over, but this point is now over here. So if you start with f of x equals 2 to the x, how can you transform it into 2 to the negative x? Well, let's go to the method that we had before. Let's review the graph. Original graph should look like this. Our graph here will be something different. So remember I said if you have a negative on that exponent, a good tactic to use is to rewrite it as 2 powers. So 2 to the negative 1 times x, which can also be rewritten as 2 to the negative 1 to the x, which would actually be the same as 1 over 2 to the positive 1 to the x, which of course then is 1/2 to the x power. So wait a minute, that's actually an initial value of 1. So a is still 1 and b is 1/2. So that means that we're actually going to still go through this point when x is 0, my initial value right here, that's the y value that I care about, which is 1. But with my base as a fraction, that means it's going to be decreasing. And so I actually end up with the graph reflecting over the y-axis. Wow, okay. Now, hopefully that was logical to you. And just starting to sketch these graphs, you'll get better at it. But the other thing that you can do is decide to sort of adopt the thinking that when you have a negative exponent, that will always have the effect of a reflection over the y-axis. Okay, so we'll get some more practice with those. Lastly, how can you start with 2 to the x and transform it into 3 times 2 to the x? Thinking about it graphically, our original function comes like this, and the original value, the initial value, was 1 for that plain old 2 to the x graph. So what happens when I multiply the whole thing by 3? Well, 2 to the x, that gives me my y values, and the x's are just marching along here. So that means I've got these y values from my original that I am now multiplying by 3. So whatever this was, it gets multiplied by 3. This one gets multiplied by 3. This one gets multiplied by 3. And so now the effect is a vertical stretch by a factor of 3. And 3 not only does a vertical stretch, but we can also refer to it as the initial value. And hey, that kind of makes sense because when x is 0, 2 to the 0 is 1, and I'm just left with 3 as my starting point here. So when x was 0, my new y value is 3 instead of 1 because I have done this transformation. All done.